Hello everyone. In this module on next generation fibers, I am going to discuss the approaches for designing next generation fibers. This module has been divided into 4 parts. In the first part, I will be talking about the introduction or the definitions, the classification of next generation fibers and their developments. In the second and the third part of this module, I will be talking about the approaches for designing PE gel fibers and aramid fibers. In the last part of this module, I will be talking about stimuli responsive fibers and very particularly temperature responsive textile fibers. The first part of the module, which I said, deals with the introduction, classification and basic definitions and developments. So, as all of you know, the first natural fiber was cotton, wool and silk. As you all know, the initial natural or commodity fibers in textile were cotton, wool and silk. These fibers have a very special aesthetic feel. Later on, the synthetic fibers such as nylon, polyester and acrylic were developed. All these fibers are known as first generation fibers. The cotton, wool and silk have relatively poor tensile strength and modulus, but the nylon and polyester fiber can be made with a GPD of about maximum GPD of about 10, and these can be used for various industrial application. But almost 100 years ago, when these nylon, polyester kind of synthetic fibers were not available, it was cotton, wool and silk itself were used for these kind of industrial applications. Today, we have another variety of fibers or another category of fibers which have a much higher strength and modulus compared to these first generation fibers, and these are second generation fibers, and in this category we have Kevlar, Nomex, PE gel fiber and carbon fiber, etc. These fibers have very high mechanical properties and they are not used for apparel kind of applications, but they are used for other structural applications. If we compare the properties of first generation and second generation fibers on this graph, on this, if you see on the x axis I have the strength based on the volume, that is in GPa, and on the y axis I have plotted the strength based upon the weight. So, if you see over here steel, which is a metallic fiber which has a very high density, so it has got much less strength with respect to weight. And on the other hand, if you look at high performance polyethylene, which is an organic fiber, it is a polymeric material, it has much lower density. So, therefore, it has very high strength both based on weight as well as on volume. And if you notice, if we are moving from the commodity materials to these materials, the high performance materials, the strength increases substantially. These materials like Kevlar, Nomex, carbon and PE gel fibers, because of their high mechanical properties, that is high strength as well as very high modulus. They are used for applications in aerospace, in ropes, for making bulletproof jackets. They are also used for making superior civil structures. They can also be used for making composites with epoxy as well thermosets as well as thermoplastics, and some of the examples of these high strength material are you can in composites, very high performance composites which can be used for various applications. They can be used for technical textiles, that is for mooring and towing ropes, sails, cloth, etc. And they can also be used for geotextiles for laying a polymeric layer or a film under the roads to enhance their performance properties. Besides these, many of these materials are also used in protective textiles, that is, it can be protection against fire, that is a flame retardant material. It can be protection against bullet. So, bullet proof vests or armors are also made. It can also be made used for making cut resistant apparels, gloves, etc. The high performance fibers generally are characterized by either high strength and modulus or high resistance to heat and flame, and the third category is high resistance to chemical agents which normally degrade the normal conventional fibers. But in this particular lecture or in this particular module, I am going to basically talk about materials which have high mechanical properties. Okay? And many of these materials which have high mechanical properties, they also have high resistance to heat and flame. So, the first question that arises is, what are the factors which determine the strength of a fiber? When I am talking about designing a high mechanical property material, I must understand that. The first thing is, it should have a strong and continuous bonding in the axial direction. It should not have any rubbery regions or defects in the system like normal polyester and nylon fibers. And third, the most important is also that none of the special features like convolutions etc., which are there in cotton should be present, which lead to the low stiffness or lower modulus values. So, for design of these materials, for design of high performance properties in these fibers, I would say we should have polymer chains with extended chain conformation, and there should be a strong chemical bonding in the main chain. Also, if I have polymer chains with small cross sectional area, it would be possible to pack more number of chains in the small cross sectional area. That means, more number of polymer chains can bear the load or share the load. So, that would further lead to enhanced mechanical properties. Last but not the least, there should be reduced defects or no defects or flaw. When I say defects or flaws, what does it really mean? Defects means there can be rubbery regions, or there can be impurities, or there can be chain end kind of defects. So, that means we should avoid such defects. And as per the Staudinger, a polymeric fiber structure which has polymer chains in highly extended form with very high molecular weight and highly oriented along the axis of the fiber with minimum defects is likely to result in high mechanical properties. So, this is the basic philosophy for designing the high mechanical properties in high performance fibers, and we are going to discuss this. So, this can be achieved by two different approaches. The first approach is I use a polymer which is highly flexible. That means, it can be easily drawn and it can be extended along the fiber direction, right. That means, a material I am using the ease of pulling the material and drawing it and extending it in the direction of the fiber axis. And that is possible because if the material is highly flexible and it is inert, it does not have interaction with side chains, it does not have interaction, interchain interaction, then the super drawing will be possible. And on this basis, I will be discussing in one of the parts PE gel fibers, which is based on this very approach. The second approach for achieving the same thing is totally opposite. It is contradictory to this. In this approach, we actually use intrinsically rigid interactive polymer chain. I have underlined the word intrinsically rigid interactive chain. What does that mean? That means by nature the polymer structure is rigid. What does that mean? That means the polymer structure has rigid units like aromatic structures, heterocyclics or fused rings, and many of these also have an interaction between different chains. That means, they have a strong interchain interaction and they are intrinsically rigid. So, this is the approach which is generally used for making fibers like Kevlar, Nomex, etc., that is rigid rod fibrous materials, and we will be taking it up in the third part of my module. Besides having the high performance properties, these days textiles are required to be useful for additional functions as well, that is other than their basic textile properties. Besides these days in the next generation, the textiles are also required to perform additional functions, that is other than the normal textile function. What is that? That is, they should be smart and responsive. Smart and responsive. That means, the fibers that can respond to the environmental changes such as temperature, pH, etc. And not only respond, they should actually be able to respond to that stimuli and judge the extent of stimuli and also adopt accordingly. So, if we have materials like these, they can be used for various kind of sensing applications, right. So, in this particular section, that is in the last part of this module, I will be talking about very specifically stimuli sensitive polymers which respond to temperature based stimuli, and we will be discussing them in detail. Typically, the stimuli sensitive polymers can respond to either physical stimuli like temperature, electrical energy, magnetic field, etc. You can also design polymers which can respond to chemical nature of the environment. What is the chemical nature? Chemical nature means it could be either electrolyte concentration or it could be the pH of the medium or the environment. But as I mentioned, I am going to take an example of temperature responsive polymers and discuss with you the strategies to make fibers from temperature responsive polymers. So, these fibers will be suitable for various kind of sensing applications, etc. In the next module, in the next part of the module, now I will be talking about the PE gel fibers, that is the first approach for making the high mechanical properties materials. Thank you.